So things like corn straw, wheat straw, forestry trimmings, like all this stuff that would rot and go back into the atmosphere, we sort of catch it at that point before it rots. And we do something called pyrolysis. So we basically cook it really, really fast to 500 C. So basically imagine flicking water on a pan and it goes, except now you're doing it with biomass. So you're taking little like sawdust or whatever, and you're flicking it on this 500 degree C pan, and it goes and it turns into smoke. And then we condense that smoke into liquid smoke and then inject that liquid smoke deep underground into old oil and gas reserves, old oil and gas formations. And so, the CO2 is coming out of the atmosphere into the plant, ending up in this liquid deep underground. So that's the carbon removal pathway. What's crazy is that liquid smoke is actually liquid smoke. Like if you've ever cooked using liquid smoke, it's like the flavor in barbecue chips or barbecue sauce. So we're actually making something that can be turned into a food ingredient and using that as our kind of carbon capture medium.
Welcome to the Curiosity Podcast, where we go deep on a wide variety of technical topics with the smartest leaders in the world. I'm Immad and Rajat, co-founder and CEO of Mercury, and I've invested in 300 plus companies.
And I'm Raj Suri, co-founder of Lyft and Presto Automation. And today we're talking to Peter Reinhardt, who has co-founded a company called Charm Industrial, which is doing some really interesting work in the carbon removal space. This company was just only recently founded, but is already capturing thousands of tons of carbon dioxide. Emma, what did you think of this conversation with Peter? I mean, he's working on something that is kind of a booming industry, but it's a very difficult technical problem, dealing with really atoms and not bits. This guy's come out of 10 years working on software companies.
Yeah, I really love it. I mean, he's obviously super thoughtful about this problem. He goes into lots of other technologies and he's really thought about it from first principles. And I think you need that kind of experience where, you built a scaled up company and now you're applying it to a completely different space. And it's just so obvious that he's so passionate about it.
What really interests me about Peter, very thoughtful about these different technologies, but also really good about boiling it down in simple terms so everyone can understand it. There's very complicated chemistry and logistical, mechanical engineering topics, boiling it down so lay people can understand it. I thought that was really quite valuable. And just understanding the space, which is really growing dramatically. I mean, we just saw a big deal with Microsoft that we'll talk about, committing to remove thousands of tons of carbon. And this is going to become bigger and bigger as we see more companies commit to carbon removal. So yeah, very interesting conversation, very timely as well.
So let's go to Peter and learn more.
Peter, it's great to meet you. We haven't met before, so I see you're a fellow MIT guy. I think we overlapped for a couple of years there. Excited to talk about what you're building.
Great to meet you too. Thanks for having me.
I guess first question, what's your background and how did you get started on Charm?
Yeah, I grew up in Seattle and I was a huge math nerd and then went off to MIT and studied aerospace engineering and kind of thought I'd always go off into like the aerospace rocketry side of things. But I got kind of my first exposure to government working with the Navy at the Naval Postgraduate School and was just horrified with the bureaucracy. And so that sent me kind of careening towards startup world. And I ended up dropping out with my roommates and started a software company. And it was about halfway through that journey, about 5 years in, that we were maybe 50, 100 people, and we decided that we were going to remove some of our offsets or remove some of our emissions through offsets. And, we purchased some offsets with, Amazon rainforest protection and Indonesian rainforest protection, and I was pretty excited about that. And then a year later, we went back and looked, and we were like, okay, what happened? We spent like 20 grand on this, what happened? And the deeper that we got into that, the more we were like, I'm not sure anything good happened. I don't know if any actual carbon impact happened here. We had set aside, some acreage in a rainforest, but how do you know that it didn't get cut down next door? How do you know that it didn't burn up in a fire? It's really hard to make guarantees about forests, especially when you're saying those forests are going to stick around for 1,000 years, which is longer than any civilization has lasted previously. So these are tough guarantees. And I was disappointed. And so I fell down the rabbit hole of how do you build a better carbon removal? And, I guess 7 years later, here we are, still falling down the rabbit hole.
So it wasn't the case that you thought that you were like scammed. It was just like the median of like carbon removal was like just not great in a forest.
Yeah, I don't think people are scamming. I think that well-intentioned people are trying to protect rainforest, but doing it with like very inadequate mechanisms for doing so. And since then, a lot of the research has been borne out. Berkeley Carbon Trading Project found that 95% of the offsets that are purchased like do nothing. There's been like scandal after scandal after scandal in ProPublica and Tech Review and Bloomberg and so on, showing that most of these projects don't actually do anything because of leakage.
So you approached this problem. You were like, okay, it turns out I can't actually buy carbon removal. What was the next step? Like, how did you go from that to kind of building this company and also this particular kind of iteration of like the problem?
I was fascinated by it, first off, and I always wanted to get back into hardware because I came from this aerospace world and kind of fell backwards into marketing technology with Segment, but was way more excited about hardware and the physical implementation of infrastructure and moving things around out in the field. And so I spent about a year of Saturdays in 2016, 2017. Every Saturday, like going through a spreadsheet, building out a model of like, what if we tried this pathway? What if we tried that pathway? For doing carbon removal, and eventually settled on kind of a narrower theme, which was, is there an industrial process where we could just make the industrial commodity, steel, cement, methanol, like something like that, an industrial product that we could just make at lower than current prices with a process that sequestered carbon along the way? So could you like redesign the process so that it sequestered carbon instead of emitting it? And if you could, then that'd be awesome. You could just like scale to the commodity scale, but be doing the reverse of the problem that we have. And so eventually settled on a pathway that looks like it might, which is to take biomass and cook it in different forms and leave behind some carbon in the soil or underground, and then use some of the biomass energy for some of these chemical or industrial processes. So that was kind of the framing of it. My co-founder, Sean, really had the key breakthroughs at the end of 2019 and 2020, about 2 years into starting the company, that led to our products today around bio-oil sequestration. But the sort of vein of industrial decarbonization that does the reverse of emissions was the key kind of vector we were tracking.
Walk me through the process from like, where does the biomass come from and where does the end thing end up?
Yeah, so the process that we do today is, CO2 is coming out of the atmosphere every year. 100 billion tons of CO2 comes out of the atmosphere into plants all over the world, algae, et cetera. And then those plants die, rot, et cetera, and 100 billion tons goes back into the atmosphere. So there's a huge like lung action that's happening every year. What we do is we basically take the residues, so things like corn straw, wheat straw, forestry trimmings, like all this stuff that would rot and go back into the atmosphere. We sort of catch it at that point before it rots. And we do something called pyrolysis. So we basically cook it really, really fast to 500 C. So basically imagine flicking water on a pan and it goes, except now you're doing it with biomass. So you're taking little like sawdust or whatever, and you're flicking it on this 500 degree C pan, and it goes, and it turns into smoke. And then we condense that smoke into liquid smoke, and then inject that liquid smoke deep underground into old oil and gas reserves, old oil and gas formations. And so, the CO2 is coming out of the atmosphere into the plant, ending up in this liquid deep underground. So that's the carbon removal pathway. What's crazy is that liquid smoke is actually liquid smoke. Like if you've ever cooked using liquid smoke, it's like the flavor in barbecue chips or barbecue sauce. So we're actually making something that can be turned into a food ingredient, and using that as our kind of carbon capture medium.
You're not so much capturing the carbon from the atmosphere, you're actually preventing carbon from going back into the atmosphere by doing this, right? You're catching it at the right time.
It depends where you draw the system boundary. Yeah, you can look at it as like, no one today says that every time a field gets chopped down, every time someone harvests their field and that stuff rots, no one counts that as emissions because it's cycling so fast. But yeah, if you were to count that as emissions, then it would be a massive emissions sector in the US. And then it would be a reduction, I guess. Yeah.
Yeah. I've seen a lot of efforts, and I actually worked on one in university myself, where to convert this biomass into biofuels, and like you might have seen some of the things like that, like cellulosic ethanol and things like that. Is that something you looked at and rejected? That was supposed to be a big form of being relatively carbon efficient energy generation at some point.
I mean, a big portion of gasoline that we consume is cellulose, or not cellulosic ethanol, but corn-based ethanol. Cellulosic ethanol, when you make it out of corn, you're really using like the starch and the sugars, as you know, in the corn kernel. Cellulosic ethanol, where you take like the rest of the stalk and the cob and like all these other parts of it, and you try to convert that into a fuel is much harder. And part of the reason is that it's just not, the material is not that energetic. It's not nearly as energetic as crude oil or these other things. Just the energy content per kilogram is like a third of crude oil or natural gas. So it's really hard to upgrade it. Like chemically, you're trying to pull oxygen out of it, which means that you're going to be using up lots of hydrogen, which means you're going to be doing electrolysis or something to generate hydrogen to then have the hydrogen, pull the oxygen out and leave behind a more energy-rich fuel. So it almost ends up being an electrofuel, except it's a really messy chemical process. And there's other chemical approaches like anaerobic digestion and other approaches, but they all have struggled, I think, to make the economics work on the basis of fundamentally the energy in the biomass is not that high. And so that's actually a key philosophical thing in what we're doing, which is we're not using the biomass as a fuel. We're using it actually for its carbon value, which when we first did it, a lot of people in the industry were kind of pissed off at us, right? They're like, you're going around telling people that biomass isn't valuable as energy. We think it is. And I'm like, why isn't it exploding? And why aren't people doing more and more of it then? Like, we think the value is in the carbon. And so it's a different access to evaluate the value of it.
Why do you have to do this process where you make it super hot and kind of create this liquid gas? Why not just bury the biomass itself?
Yeah, if you're going to bury the biomass, then it's going to be close to the surface, which means it's like prone to disruption, right? How do you set a guarantee that someone won't dig it up? Is kind of part one. Part two is you can very easily have anaerobic digestion, which is something we purposely do, right? Where we take this cellulosic stuff and put it in a big vat and put it in with water and bacteria, and it turns into methane. And methane is a much more potent, like almost 100x more potent greenhouse gas than CO2. And so you can very easily accidentally have even a trickle of methane emissions, like 1% methane emissions, that then blow your life cycle completely. So, by turning it into a liquid, we can inject it half a mile to 2 miles underground, and you're never getting it back. It actually solidifies information, and so it's super permanent. And so we can make strong guarantees about its permanence, which is what our customers want. And it's in formations where it's not gonna get eaten. So it's the permanence guarantees can be much higher.
Where are you finding these deep holes? Are you digging them, or there's already existing holes?
Lots of existing holes. So the U.S. has somewhere between 3 and 5 million end-of-life oil and gas wells, and they're pretty much all applicable or potentially useful in the process that we've got. So just an absolutely shocking number of oil and gas wells across the U.S. And it's a rock formation that used to have oil and gas in it. So it's porous, it's permeable. There's an existing pipe that goes all the way down. So we can show up and repurpose that pipe that is, just instead of sucking out the oil via the straw, sort of blow the bio-oil back down the straw.
In like 10,000 years, will it become oil itself? As in, are you like recreating the cycle?
Yeah, it's a good question. Like deep history, like discovery of ancient civilizations, put it there billions of years ago or millions of years ago. Yeah, we don't know what it's really going to turn into. I think our best hypothesis is that it might be a really strange form of coal. If you look at what typically becomes oil has a C to H ratio that's or the hydrogen to carbon ratio is quite high. So you have basically 2 hydrogens or more than 2 hydrogens for every carbon. What we're injecting is closer to like 1.3 hydrogens for every carbon. And so there's no source of hydrogen down there. So that's more akin to like a brown coal maybe. But it's going to be brown coal that's like in the porous, empty places in sandstone. So it'll be a really weird, if someone goes and digs it up 5 million years from now or whatever, it's going to be a really weird substance. They're going to be like, how the hell did this happen?
So one question I have is like, okay, what drove you back in the day to do this, to actually purchase carbon credits? Obviously, it's happening more and more. How is it trending? Like, how is the demand for carbon trending, and what is driving that demand?
In most of the world, it's a voluntary market. So it is corporate buyers for the most part who are saying, maybe for recruiting reasons, for like philanthropic reasons, like we want to zero out our footprint. And therefore, we're going to go buy offsets or removals. That market historically has grown to about $2 billion per year, and was primarily offsets. So there's a key thing to understand here, which is an offset is like I emit and you emit, and an offset is I pay you not to emit. So there's still 1 ton going into the atmosphere. A removal is I emit and I pay, Charm to go remove a ton. So it's netting out to zero. And so a couple things have happened. One is people started getting uncomfortable with the idea of offsets, that it like wasn't going to be enough to get us actually to net zero, which is what's necessary to kind of limit the impact of climate change to a degree that is probably okay for civilization and ecosystems. And the second is that all this effectively fraud, even though it was well intentioned, has happened in the offsets world, where it's largely garbage. And so this $2 billion per year market is going through actually like a very dramatic transformation right now, where all that is shifting over to much more permanent carbon removals, whether that's bio-oil sequestration or direct air capture or ocean alkalinity enhancement or enhanced rock weathering, like all these new methods that have much stronger guarantees about permanence and measurability. And that transformation is underway. So like 2020 was the first year that anyone ever bought carbon removal in like any kind of material amount. And that was the Stripe, Shopify, and Microsoft as the first 3 buyers in the space. And it was to the tune of like $2 million. So that was the market size in 2020. This year alone, there have been announcements of carbon removal purchases that will be spread out over a decade, but total contract value is like approaching $1 billion in terms of total volume. So like the carbon removal portion of the total carbon credit and carbon offset market is like going nuts.
Incredible. Yeah.
And I guess it's kind of a commodity, right? Like if I want carbon removed, like you just named a bunch of different methods for removing carbon, like I just want the cheapest one, right? The whole world actually just wants the cheapest method for removing carbon. And I guess if you have the other guarantees, like it's like actually long term and it actually does remove it and all of those things.
You'd think that's not really how it works, though. Yeah. So I think eventually it will become a commodity market.
Yeah.
In the old offsets market, you basically have 2 tiers of offsets. You've got this like bulk of really junky stuff that is like 50 cents a ton. And like candidly, it's not good, but some companies buy it just to be able to check the box that like we're carbon neutral. There's a higher quality tier around like $20 to $40 a ton of nature-based offsets, which are like quite a bit more effective. But there's pretty limited volume of those. There's like very limited availability of high quality stuff there. And there it's supply limited. And then as you get into the higher quality stuff, you become increasingly supply limited. So, total deliveries of permanent carbon removal over the past 2 years, 3 years are like less than 10,000 tons.
How much do you charge your customers?
We charge $600 a ton, and we've delivered about 60 to 80% of those 10,000 tons. So the total volume, like most of that delivery is Charm to date. You have some direct air capture stuff is selling at like $2,200 a ton. There was a contract announced today where Microsoft is purchasing over the next 10 years. So there's some price curve on it at $200 million for 310,000 tons. It's like $634 a ton, but over a much longer period than what we're selling for, in the current year. So my point is there's a huge skew from 50 cents to $2,200.
Yeah, that's really interesting.
It's because it's not actually commodity, because you have these other things that layer in like co-benefits and permanence, and people want a portfolio of different technologies so that we don't down select too early and so on and so forth.
What is the biggest cost for you? Like what's stopping it going from $600 to $5 per ton?
The biggest part of our cost structure today is the CapEx for the machine. The machine that does the conversion from biomass to bio-oil. And it'll just take time for us to figure out how to make that machine better. And, our pattern is that we run the machine on one shift, and then the next shift we make some modifications and we keep iterating on like a daily, weekly, kind of monthly, it's like constantly iterating as we kind of figure out how to bring down the cost of CapEx, how to make it easier to operate so that even as we have more machines, we need fewer operators per machine to lower the OpEx to run the machine. So those are the two biggest components of cost per ton. Costs around injection or transport of the bio-oil are quite small. And over time, more and more of the cost will become the biomass itself. And so a really key part of the charm model is that the machines, the pyrolysis machines that we're building, need to be small and mobile. Like basically imagine farm equipment, like a harvester. And that's important so that you can actually go to the field where the biomass is, which cuts out 90% of the cost of the biomass. Today we'll be operating at pads, where we have a collection. We bring the biomass to the pad. And as we bring down the CapEx and the sort of OpEx from running it, the biomass becomes a big portion, and then we'll flip to on-field and cut out most of the biomass cost.
So what's the cheapest this could get to if it's literally on the field, you get the biomass, you put in a super efficient, low CapEx machine, and then I guess there's energy cost for the machine. Like how cheap does it get?
We think it can get down in the $50 to $100 a ton carbon dioxide removed range. Takes quite a significant volume to get there. But yeah, we think we can get down in that range, which is, well below the societal cost of carbon, which is like, $100 to $200 a ton probably.
Are there other technologies you look at and say like, hey, those can get, at a similar range, or do you think this is going to be by far superior?
I think direct air capture, people generally think these are like sorbents. So it's the air vacuum. You got fans or wind blowing over sorbents that are absorbing CO2, and then a heating or some kind of cycle that then desorbs the CO2 and gets pumped underground just as pure carbon dioxide. That's called direct air capture and sequestration. A lot of different companies going after that. It will always probably be more expensive because it's kind of a brute force approach, probably in like the $100 to $200 a ton range. The disadvantage there is like at the scale needed in 2050, it would be like 50% of global steel production to build something like that, and a huge chunk of renewable energy production as well. But it's the backstop. We can make it as big as we want. And so we will almost certainly need some direct air capture. Other ones that I find very interesting are like enhanced rock weathering, where people grind up basalt and spread it on fields. This one is harder to measure because you have carbonic acid, which is CO2 dissolved in rainwater. It is slowly dissolving the basalt powder on the field. And as it does that, it pops out silicon as sand and turns into bicarbonate, which sequesters the CO2 into the water, and then that flows out to the ocean. But you can imagine like you're going into this bicarbonate, which is flowing out to the ocean. There's other acids competing to dissolve it, like nitric acid. So it gets very complicated to do the accounting and measurement of like where did the CO2 go exactly. So that's the challenging part of enhanced rock weathering. It can also probably get in that like $50 to $150 a ton kind of range. And then ocean alkalinity enhancement is another interesting one. We have this ocean acidification problem. If you pull acid out of the ocean and store it somewhere, or you pump alkalinity into the ocean, then the ocean will absorb more CO2, which is really cool. The challenge with that one is, again, measurement. Like it has to mix at the surface with CO2 in the atmosphere, and those mixing times are unknown, right? It's almost impossible to model. We're like, well, it'll happen at some point in the next 1,000 years. Just like, okay, we need better models and a better understanding of that to tighten those bounds so that we can understand when the CO2 is actually going to get removed. And there's also a question there of like social license to operate, which is like people are pretty sensitive about like pumping things in or out of the ocean because we don't necessarily really understand it that well. So there's a lot of work I think that has to go into kind of social license around ocean alkalinity enhancement specifically. So there's trade-offs in all these dimensions. I suspect we will have all 4 technologies deployed at scale by 2050. The mental model here is like renewable power or clean power. It's like, it's not just solar. There's solar, there's wind, there's nuclear, there's geothermal. It ends up being a portfolio depending on geography.
Yeah, makes sense. And you mentioned the Microsoft deal. Is that basically the rock one? You mentioned the one that converts to silicon, or is that something different? With Heirloom, I believe it is.
That's really a direct air capture company. They're using limestone effectively, or the magnesium variant of it. as the capture medium, which is a rock, but they're doing direct air capture in the sense that they're cycling that magnesium hydroxide or limestone to pull the CO2 off and then inject the CO2.
Okay, got it. And what you also mentioned the societal cost of carbon. What do you estimate the societal cost of carbon is?
Well, I don't estimate it, to be clear. What I've read and kind of seen the studies point to is, something in the like $100 to $200 a ton range. I think the US government kind of tracks this and historically has looked at it at about $50 a ton, but more recently has updated it into around the $100 per ton range.
How many tons of carbon output are humans doing right now? Like, what's the estimate of that?
On a CO2 equivalent basis, because it's not all CO2. It's CO2, it's methane, it's NOx. Methane is like a third of the problem. So it's not to be ignored. But on a CO2 equivalent basis, it's about 50 billion tons a year. So as I mentioned earlier, you've got the biosphere is doing 100 billion tons of lung in and lung out every year. And then we're always emitting right now about 50 billion from civilization. So carbon removal needs to go address probably, even once we get down to net zero, order of magnitude carbon removal needs to go address about 1 trillion tons of historical emissions that has to be unwound somehow.
So if it costs $50 per ton, it would be 50 trillion tons to get that like historic addressment, right?
$50 trillion, yeah.
Yeah, order of magnitude.
That is a mammoth task.
We've emitted a lot of CO2. It's pretty crazy. And the interesting thing is pretty much all those emissions are recent. Like if you look at how much total we had emitted as a society, even like I was born in 1989, something like close to half of all emissions happened in my lifetime, or maybe even more. Like it's shocking how much is really recent.
Yeah, power of exponential growth.
Mm-hmm.
And it continues, right? Like, we're still emitting crazy amounts. I mean, even though I think the developed world has decreased our emissions, but globally, is it accelerating or is it decelerating?
I don't know the slope on total global CO2 emissions, but certainly in the US, per capita emissions have been declining now for quite a while as we've been efficiency measures, solar deployment, et cetera. I think the most recent chart I saw actually showed that the US was back at World War I levels of per capita emissions. So we're doing pretty well. Now that was, most of the exponential rise in US emissions from coal and oil actually happened pre-1915, but, we are back down to pretty far back, which is exciting. When you look internationally, one of the things that people say is like, oh, but like China's never going to decarbonize. Like, I'm sorry, that's just wrong. China deployed more solar last year than Europe and the US combined. Like just straight up, they're deploying solar as fast as they humanly can. And India is doing the same thing. So I think the developing world is going to actually skip a whole lot of, at least on the grid, is going to skip a whole lot of the fossil fuel infrastructure. Not to say that China isn't deploying coal plants, but like they are deploying solar at massive, massive scale, and probably will do the same with batteries.
And nuclear too, right? I think they're all in on nuclear, unlike us.
Yeah, I mean, as we should too. I mean, the stupidest thing happening right now is Germany, like rolling back nuclear plants under the greens to go turn on coal plants. I mean, that is just like next level brain dead. But I think France has the right thing here, right? They're like reactivating all their nuclear programs, getting ready to build more nuclear. We have some momentum on that in the US, which is exciting. The Diablo Canyon nuclear power plant got an extension. The first nuclear power plant in the US in a while got turned on recently. Advanced nuclear reactors are starting to make some progress, particularly with congressional support. So I think nuclear has a huge, huge role to play in decarbonizing the grid. It's just like the base load power is so hard to decarbonize with solar, unless batteries get really, really good. Geothermal and nuclear, I think, are going to be real anchors, but are nascent.
For an individual, it doesn't take, like, I don't emit that much carbon, right? Like, or I don't contribute that much to it. So do you have a program for like consumers to just go to Charm and buy directly and like offset themselves?
We do, yeah. You can just go to the website if you want.
Oh, really? All right, there we go. I should go after this.
Please do. That'd be awesome. What's even cooler, actually, is the opaqueness that I encountered as a buyer in the offsets world really pissed me off. Where I was like, I just want to know what happened. And so last year we launched something called our registry. It'd probably be better called Ledger. We might rename it. But if you go to charmindustrial.com, you can click on registry and you can see the history of all the deliveries that we've made. So you can just see like Joe Schmo bought X amount of tons. It was delivered on X date. You click it and you can actually see like almost a FedEx style delivery history like key dates that the injection happened and so on. And you can see the full life cycle analysis of what happened. So that's like V1. I'm really, really excited about actually doing more in this direction over time, where hopefully we can show more of what's happening in the supply chain and get to like a even better than UPS style kind of history and transparency of like where carbon is going. And I think this is like weirdly not obvious, but super important in the carbon removal industry. Actually, I want to push the industry to like do much better here than offsets ever did. Because it's a weird thing. It's an industrial process, but you don't deliver it to a loading dock, right? Like you're in someone's supply chain, but like there's no physical manifestation of it. It's like the carbon hopefully has disappeared. And so like, how do you document disappearance? Like, how do you deliver disappearance? Is like, you better document the crap out of it. So like, that's what the registry is intended to do, is like document and prove and make it transparent what's really, really happening there.
What does your operation look like? Like, how big is this like facility that's doing this stuff? Where is it? Are these like big machines? Like, what does it look like?
Yeah, the machines are not that big because, again, remember they're mobile. So people do build pyrolysis facilities, which are like, you know, almost like small refineries or something. Like that's not our vibe. Think of it as like farm equipment. Some of our equipment is actually driven like powered by tractors and stuff like that. Our main operations kind of hub is in Colorado in Fort Lupton. So our operations team that's based there. We have a mobile unit that we actually move out to deploy for demonstration purposes now in forestry settings. So we're working with like a major utility in California on demonstrating that we can consume biomass that comes out of vegetation management to prevent wildfires. And we'll be doing similar kind of like wildfire prevention, forestry residue demonstrations in the state. But really kind of the long-term mental model should be these like machines, harvest equipment effectively, following the harvest from Texas to North Dakota twice a year, once for corn and once for wheat, and processing all that biomass at the field edge or on the field, and offloading a bunch of bio oil that's getting driven less than 50 miles to an injection well.
Does the weight of the biomass like reduce a lot from this process, from like taking the biomass, turning into this fuel or liquid gas?
This is the fundamental reason to do it actually on the field, which is manipulating biomass is really expensive because it's so fluffy. So, when you just have biomass in a bale, for example, the density might be like a couple hundred kilograms per meter cubed. So like call it 300 kilograms per meter cubed. If you were to pelletize it, which is very energy intensive, that might get you to like 600 kilograms per meter cubed. So you might double it. When we convert to bio oil, the density of the liquid is like 1,200 to 1,300 kilograms per meter cubed. So we get another 2x. So we get this huge like 5 to 6x increase in density, and then a pumpable fluid. So we don't have like forklifts, slowly moving bales. You just like hook up a pipe and out it goes. So the logistics and cost structure of moving around bio oil is like way less than moving around biomass. And it turns out that's the dominant part of the cost structure.
I've heard previously this kind of, I call it a degrowther meme, but this idea that we should not invest in like carbon removal technology because that encourages people to keep pumping carbon out. Is there any merit to that, or are you just like, that's stupid?
Unfortunately, there is one oil and gas company that has effectively made this their mental model. And the comment from the CEO was on a podcast was like, our intention is to sequester CO2, use it for enhanced oil recovery, and our goal is to pump the last barrel of oil out of the ground. Like that was kind of quote. And like, that's super frustrating, candidly, because in any of the models, that's not really the role that carbon dioxide removal plays. It can't really get to that scale and kind of economics to remove any appreciable amount of CO2 that we're sort of actively emitting on an ongoing basis. It's just not cost effective to do that. And it's like our only recourse for historical emissions. But for going forward, we have to be reducing super quickly. So when there are opportunities to reduce, we should like take those absolutely. Unfortunately, when you look at the emissions we've already done, it's in excess. And so especially then when you look at like the best possible like reduction curves, there's going to be a whole area under that curve of like CO2 that has to get removed from the atmosphere. And, it's already up there. So we got to go back and remove it. But yes, we need a very steep reduction curve. And, that one oil and gas company aside, which is Occidental Petroleum, the carbon dioxide removal industry as a whole is like not talking about it that way, or not using it that way. And most customers are not using it on that basis. They're mostly thinking about historical emissions that they can't abate any other way.
Are you mostly kind of supply constrained right now? Like you just can't scale this up quick enough, or is it supply and demand because like the price is quite high right now anyway?
We're entirely supply constrained. So we've sold order magnitude 140,000 tons of removal. And we're entirely supply constrained. We've delivered 7,000 of that. And within supply, we're not constrained on injection. We're not constrained on biomass. We are constrained on pyrolysis capacity to convert the biomass into the biooil. And there's often a more academic concern of like, but is there enough biomass out there? Everyone's talking about using biomass. And talking about using biomass and actually using biomass are two very different things. We get calls from CAL FIRE and US Forest Service and others, where like, we have a 6-mile long pile of logs, like that we had to remove to prevent wildfire, like, or because a wildfire happened and we were removing it so that forests properly regrow. Like, can you do something with it? It's like, I'm sorry, I don't have the conversion capacity for a 6-mile pile of logs. So, the amount of biomass that's out there is staggering. We probably get an email a day of someone who's trying to offload waste biomass to us. But yeah, we're constrained on the capacity to convert.
I had a question just about building a company like this. I mean, this is obviously very different from what you've done in the past. Probably very different, like capital structure, like, employees that come and join this type of company. The technology that you're building is completely different. I mean, is it basically night and day compared to like building a high growth software company, venture backed company, or like how is it different?
Yeah, and I guess to clarify my sort of prior experience with Segment, high growth software company, grew from 4 founders to 600 people over 10 years, and then sold the company to a public software company called Twilio. The differences are stark in some places and extremely similar in others. So, like finance, fairly similar, like expensing policies and how do you do reimbursements and how do you do a long range plan, and like it's pretty similar. HR, pretty similar. Recruiting, pretty similar. So a lot of the G&A functions are pretty similar. Even things like, project management, just managing a team in general. How do you run like a high functioning leadership team? Like all those things carry over well. So there is a lot of like common infrastructure that can carry over. There are some places though where it's just like wildly different. I think hardware development is wildly different than software development. And the second and third order effects of those differences are pretty pronounced. In software, when you want to ship something, you go to, or you need to like have a new piece of code in your stack, you go to GitHub, you find the right library, build it into your code, and you ship it and test it, whatever, boom, it's live. You can all be in one day, right? There's no supply chain that like delivers the repo from GitHub by CD. But when you go to make hardware, you have a lead time, right? Like, you want this blower? Great, this blower has a 4-week lead time. Someone's got to make it, someone's got to ship it. Like, it physically has to move somewhere, and atoms have to move around. And so 4 weeks is like not a bad lead time. You could easily get to 13 weeks or 16 weeks when you get to these like big bulky transformers that might be needed to update a facility. You could be talking about like 18 months lead time. So when you have these longer lead times, you physically cannot iterate on something often on like a daily or hourly kind of time scale. And so that means that you need to parallelize basically. Like parallelism is how you can achieve more learning in the same amount of time, where you could build one machine over say 18 months, or you could build one machine and buy 2 machines and evaluate all 3 at the end of 18 months. So you get 3 learnings for the price of 1 in terms of time. And that's great. It comes at a cost of now you're managing more complexity because you're trying to manage 3 things in parallel. It comes at like, that's the second order effect. The third order effect is like, if a team is building something internally, but the thing that you bought externally turns out to be better in the end, how does the team internally feel about the thing getting shut down? Like, So now you have a third order morale impact. So there's all these things that flow out of like building a physical thing and testing a physical thing has lead times to it. Another example is like a debug statement in code, right? Like, I want to know what's happening on this line. Great, add a println statement and like print out the variables, what's happening. Okay, but like you want to know what's happening inside the reforming vessel. It's like, okay, well, you need a whole nother piece of test equipment that like has some elements of what's there, but is missing the other elements, say like doesn't have oxygen so that it's not burning. And so then you can like study droplet sizes or whatever. It's like peeling apart what's going on inside of a hardware system is way more complicated and requires a whole nother engineering effort in a way that software can often just drop in debug statements or tracking statements. So a lot of those things are very, very different and have all these sort of complex ramifications in terms of how you manage execution.
What about like things like you're working in a different space altogether? Is like the employee type different? I mean, one in a tech world, in the software world, you have software engineers. But now you probably have very different types of employees. You're also managing logistics. So how does the talent pool differ?
Yeah, I think a lot of the engineering and sales and policy and operations, at least on the management side, is pretty similar to other tech companies. I mean, it is different in the sense that it's mechanical engineering and there's like a different set of top schools, and we're hiring people that are coming out of ag tech or food tech or aerospace as sort of like common areas. So it's subtly different in that way. The biggest difference by far is when you go to shift work on having like a team of operators who are actually operating equipment. And then you get very quickly into like, really like training around safety in particular. Like how do you manage non-exempt versus exempt and all the compliance and payroll that comes along with that. When someone's working on a shift, you can't just like not run the machine, but all hands is happening. So, like all these things, the mechanisms and ways that people, they might be in a location that doesn't have great internet. There's like so many things that we kind of take for granted in a more typical workforce or team in a tech company that kind of break down there. So that's its own challenge and something that we're figuring out as we scale into it.
How do you think about the role of government? I mean, we're talking about trillions of dollars. Obviously, the government has that. Biden just did the Inflation Reduction Act, which was not about inflation, but I believe it had actually some stuff around carbon removal. So, was that helpful? Like, how do you think governments will be involved in this project?
Yeah, governments, I think, are going to play a very big role. Actually, our first leadership team hire was a head of policy for this reason. Like, that is pretty unusual. No software company has like first management hire is policy and government relations and lead. So very important. The Inflation Reduction Act had two major things that created funding for carbon removal. However, both were very narrow. So they specifically created funding for direct air capture into saline aquifers. So this is like the most narrow version of direct air capture. And the two mechanisms were like roughly $3.5 billion of 50-50 split on CapEx for direct air capture plants. So if you're going to go build $1 billion direct air capture plant, government has an application process, but they'll effectively cover half of that capital cost. And then it's cost share with the other 50% coming from the company and investors. So that was one bucket. Again, very narrow to just direct air capture into saline aquifers. All the other mechanisms, including bio-oil sequestration, not included. The other mechanism is a tax credit called 45Q, which is $180 a ton for direct air capture into saline aquifers. And then $80 a ton for flue stack capture of carbon dioxide into saline aquifers. So again, very narrow, but quite a compelling incentive to start delivering CO2 underground. So yeah, I think it is already having a pretty big impact on the space, but I think the challenge for the government is basically like how to make it tech neutral so that we can get the biggest bang for our buck in terms of making sure that we're taking a portfolio approach at the government level as well.
Why did they choose that particular tech? And I guess, was that frustrating for you that like they picked someone else's tech?
I think it's just representative of it being like the incumbent, I guess. Direct air capture was really kind of invented as like a concept for this like 15 years ago, maybe longer, but like a long time ago in sort of academia, and then has like had a long time kind of bubbling between academia and the policy sphere to turn into policy. Whereas bio-oil sequestration, enhanced rock weathering, and ocean alkalinity enhancement, all much newer. And so there's an education time to come up the curve on those things.
Got it. And I assume you think if there was a Republican in power, there would be like way less support for any of this stuff, right?
There's a lot of Republicans who had really key, strong positions in support of carbon removal and carbon sequestration. A lot of the states that expect to kind of see it deployed in mass are like Louisiana, Wyoming, North Dakota, Texas. States that are solidly red. From an economic transition perspective, it's a huge continuation of employment. Of all the jobs that exist in the oil and gas sector today are probably pretty relevant to doing the reverse in terms of putting CO2 or bio-oil underground. So it's a huge economic opportunity for a lot of these red states as well. So it's not really a partisan issue.
But I mean, in the government, I mean, the Republicans, they still like don't fully believe in like climate change. I mean, I know that maybe that doesn't filter to like the economic incentives on the ground when it comes to like government money, but certainly that must make a difference, no?
I know that those are the public talking points that get spread in the mainstream media and probably on Twitter and so on. I've spoken with a lot of folks on both sides of the aisle in DC. I think it's a very small minority that are actually don't believe in climate change. Like the position is basically one of no one wants to do wrong by the environment. Like I like hunting, I like fishing, I like being out in the wild. Like it's an important part of how I grew up and how I live my life. It just has to be economically feasible. Interesting.
So you're saying there's a disconnect between what people use as talking points for politics versus actually what how they act.
For sure. On both sides, but yes.
Yeah, got it.
Do you find more rational and better support in Europe, where it seems like they're really bought into trying to alter climate change?
Europe was much earlier on the scene, right? They have been making a bigger push on climate for decades, because of some of the different politics going on there. A lot of money has been spent. It is not clear that Europe is ahead. Especially after the Inflation Reduction Act, a lot of companies who are based in Europe basically shifted their deployment focus to the United States. It's not clear. I've had some conversations, and it's just a pace thing. It's like a pace of development, a pace of execution is just wildly different in the U.S. I talked to one person who was a board member of a European clean tech company, and I thought this was quite sad in a way. I mean, like encouraging to me personally and to Americans as a whole, but quite sad. He's like, we work at this for many decades, but in the end, when the Americans show up, we know it's really going to happen. and it's like I'd hope you could just kind of do it, but the pace is wildly different.
Yeah, maybe there's a little bit of a late mover advantage as well. Is there some science or technology that like is maybe in research right now, or maybe no one's come up with it that like you think could substantially change the situation when it comes to carbon removal, carbon capture?
I mean, there's an explosion of carbon removal technologies and companies over the last few years. If you go back to 2020 when we kind of started into the space, there were, I don't know, like a dozen companies or something like that. There's probably like 100, 200, and like a flowering of like interesting approaches. Frontier Climate, which is a $1 billion aggregate fund that to purchase carbon removal, pulled together from Stripe and Shopify and McKinsey and JP Morgan and Facebook and Google. They just announced their sort of most recent tranche of purchases this morning. And it's a really interesting set of like a dozen companies with like very creative approaches. I don't know that there's going to be one that's like 10x. Like, I don't know that there's going to be one that's like, we can do it for $5 a ton. Just like thermodynamically, that's very challenging. Even to get under $100 a ton is probably like the thermodynamic limit of like the brute force approach, which is direct air capture, where you're just like, screw it. We're just going to use power. We're going to get rid of the entropy and consolidate 400 parts per million CO2 into a pure stream and shoot it underground. That's like brute force. Like, don't take advantage of any sort of other processes happening. That gets you maybe down to that $100 a ton, but to get below that, you have to be taking advantage of some kind of natural process that's happening. Enhanced rock weathering, ocean alkalinity enhancement, and bio-oil sequestration all do that to some extent, right? We're relying on some element of the carbonic acid in the rainwater for enhanced rock weathering, biomass growing for bio-oil sequestration, the ocean surface area mixing for ocean alkalinity enhancement. And so those can get cheaper, but they, to some extent, pay the price that their maximum scale is tied to the natural process that they're drafting on. And so there might be some natural processes that go even lower on the cost, but they will probably be narrower and therefore like more constrained on scale, would be my guess.
I read somewhere, which, I should probably check my sources before saying this, but like apparently the trails that these big container ships were making were cooling down the oceans, and they recently changed the law about how much sulfur is in the oil or something, so they stopped making the trail, and that's why this summer was the hottest it has been in the ocean for like many years. I don't know if you saw the graphs. I don't know how verified that story is, so someone should check me. But on a high level, what are your thoughts on those kind of geoengineering projects? It seems like we've never tried to cool down the earth like actively, and it might be possible.
So I don't know that we can know for sure that like the temperature this year is an outcome of that change per se. Like that line is very hard to draw, but we do know that when we burn fuels that are high in sulfur, it turns into sulfur SOx, which is like SO2 and SO3, and so that those sulfur oxides, the SOx compounds, do have a cooling effect. We know that. We can study it in like volcanic eruptions and so on, where you have like massive plumes of sulfur oxides get emitted, and then we can measure the effect on sort of global temperature and so on. So we know it has those effects, and we know that we are burning, and we know what those concentrations are. So we generally speaking can know that there has been some kind of warming effect in aggregate from that change in fuels. I think that's real. The challenge is that it has a very local effect. It has a very local cooling effect. And so that has really complicated implications for weather patterns, and weather patterns have huge implications for like moisture content, other weather patterns and climatic patterns like monsoons and other things. So when you think about the potential ramifications of large scale SOx deployment, for example, or any kind of cooling effect like that, you really have to understand what these full set of ramifications are. Otherwise, you may really shoot yourself in the foot. To some extent, we're running the experiment, I guess, right now, in that we, over time, ramped up how much SOx we were emitting, and then we like cut it off with a change in sulfur content of fuel. It's a pretty dangerous experiment to run. Like huge numbers of farms don't rely on irrigation from underground water sources. They rely on rainfall. And so like you could have really dire human impact from these things unless you really have an understanding of the underlying like wind and moisture models and so on. So that's really the gap actually, is the gap in the science is not whether or not it has the cooling effect. The gap in the science is understanding the full set of implications before we run a large scale experiment on like, billions of people.
What do you think of this? This is getting to crazier ideas here. But I like this idea of like putting something in the Lagrange point between Earth and the sun to make it like a little bit darker here. What do you think of that idea?
I think it carries some of these same risks.
Yeah.
So yeah, it just carries risk that we don't know what the full set of implications is, and it might turn out to be great. It won't solve things like ocean acidification. Not that it needs to solve all problems, but like just to be clear that there are other problems that it definitely will not solve. And ocean acidification is its own like ramp of like coral destruction and like other mollusks. Anything with a shell like is going to start having problems. You can have other major changes in the ocean. So just to be clear, it doesn't solve the whole problem. It might help and it might simplify the problem in a lot of ways. But we should have people studying it. We should absolutely have people studying it. So I think like the number one push in this kind of geoengineering direction is like we do need government funding and social acceptance to go do the study and like find out what the implications are, because it would be dumb if we just like scared ourselves out of doing the research to understand what the effects would be.
But it is a fair point to say that like anything that would have a global effect will have some unintended consequences that like maybe are just hard to kind of figure out. We can hardly
Totally.
predict the weather.
Totally. I think the challenge with SOX is like you can go do the thing with not a lot of money. And so because of that, we almost want to invest quite a bit of capital and money in understanding the implication, maybe even more than it would cost to do the thing, which is weird just because the potential cost of the impact is so high.
Oh, really? Like how cheap is it?
I don't know the numbers off the top of my head, but from just a cooling perspective, I want to say like in the billions of dollars, something like that.
Oh, wow. That is crazy.
Like that's almost the challenge of it, is that it's not yet well enough studied, I think, for most people to be comfortable with it. But you could have a rogue billionaire just like go do it. That's what's scary about it.
Yeah. Hopefully they'll need someone's approval.
The major downside for that would be the acid rain, right? Is like the major problem.
That's the short-term hard trade-off, which is, you definitely get more acid rain for the cooling. There's these other trade-offs of like, if you're cooling some area locally, you are definitely going to change the moisture patterns, which then has other ramifications.
Interesting. How are you enjoying this this second act, I guess? Just personally, I'm just curious about how you're enjoying it as an entrepreneur and technologist.
It's way more fun. I really loved the people that I got to work with at Segment, and like that was like the guiding light and the thing for me. At Charm, I get to work with amazing people again, but I also get to work on like a mission that I really care about. And there's something magical about really working on hardware that you can see, touch, feel, and hardware that changes every day. Like, between yesterday and today, walking out in the backyard and seeing a reactor test stand coming together, it's just like, it's awesome. It's like real things coming into existence. So I love that.
A lot of people who went to MIT have the same bias towards working on like hardware. The hardware stuff was way more complex and I felt more risky financially, but actually more enjoyable.
Yep, 100%.
This is awesome, Peter. Appreciate you coming on. I think this is really, really interesting content. I'd love to pop over to your SF thing at some point and check out your production.
Yeah, please do. Come by. It's fun. It's really fun to show.
This was great, Peter. Really impressed by what you're building. So great to meet you.
Yeah, likewise. Thank you.